Hello everyone and welcome to the vibration lab. In this experiment, we are going to learn how can we measure the internal damping coefficient using accelerometer and oscilloscope. So this is my setup. I am having a cantilever beam and accelerometer is attached at the tip of the cantilever beam. The accelerometer signal is first sent to the charge amplifier and through the charge amplifier I am sending it to the a free vibration to my beam, the vibration signals will be there on the screen. And as I know, there will be a damping in the system. So when I will excite the system and I will allow the system to vibrate freely to time. When I will apply the philosophy of logarithmic decrement, I can measure the damping coefficient of the given material. We can find the damping coefficient for different material. For example, I am having a wooden strip or a plastic strip or iron strip, but I am going to demonstrate everything with this aluminum strip. And if when you will do your experiment, you can try with different material and you can find the internal damping of these materials. So before I go and start my experiment, quick review of logarithmic decrement. A real-life system can be represented as a simple single degree of freedom system. Here I am representing a cantilever beam with a tip mass as a mass connected with a damper and the spring. If I will allow my system to vibrate freely, this will be my typical plot, and here we can see that the amplitude is decaying with respect to time because the damping is presented in your system and the decay is following an exponential curve. If I will write the equation of motion of my system, I can see that here the first equation is representing the force balance equation and right side 0 is saying that it is a free vibration condition. The second equation is the response of the system. Here zeta is your damping coefficient, that is what we are trying to find through this experiment. Omega n is your natural frequency, that is simply under root k by m. Omega d is your damped natural frequency and t is any time instant. So if this is my typical plot and suppose I am selecting 4 devices where my amplitude is maximum and marking is 1, 2, 3, 4. If I will measure the time gap between these two T1 and T2 instances, I will find that this is nothing but my time period. Similarly, if I will consider the amplitude of the 4 peaks as x1, x2 and x3 and x4, and if I will take the ratio of first and second peak, after doing some mathematical rearrangement, I will land on this formula where x1 by x2 is representing the ratio of the two amplitude. Hence, after doing further mathematical rearrangement, I will land on this formula where log x1 by x2 is representing a formula that is nothing but your logarithmic decrement. Using this formula, I will be able to get the damping coefficient of my system. Here I have considered first and the second peak, but this formula is valid for any two consecutive peaks. For example, I can take the x1, x2 or 2 or 3 or 3 or 4. But suppose instead of taking two consecutive peak, you will consider first and the third peak. In that case, the formula will not correct. What we need to do, we have to add another multiplying factor in our formula. For example, you can see here that for x1 and x3 I have multiplied 1 by 2 in my formula. Similarly, if I will take the first and the fourth peak, I have to multiply 1 by 3. So you can understand here that whatever peak you are considering in between, how many cycles are there, that has to be considered for this multiplying factor. For example, if I am taking the first and the third peak, that means there are 2 cycles completed between peak 1 and 3. Therefore, I am writing here 1 by 2. 2 means how many cycles I have completed. Similarly, in the second case, I have considered first and the fourth peak, and in between these 2 points there are 3 cycles completed. So I am just writing here 1 by 3, and this is really important whenever you are dealing with some experimental data, because what happens in most of the cases when you are taking experimental signal, it is not easy to find a significant decay between the two consecutive peaks, or maybe after 1 or 2 or 3 peak you will not be able to see a significant gap and you will not be able to measure it practically. So what we can do here, we can take one peak and after some 10 cycles or 20 cycles or 5 cycles, based on the data, we can select the peaks, and then by applying this formula where x1 will be the first peak, xn plus 1 means the peak that is we are taking as the last peak, and 1 by n will be the number of cycles between the two peaks. So using this formula of logarithmic decrement, we can calculate the damping coefficient of our system. Normally we are having a vibration signal, and if there is a damping in the system, the vibration will be a typical plot of your vibration signal. And if I am going to of two consecutive peaks, I will be able to get the damping coefficient. So let's start our experiment and try to find the damping of aluminum strip. Here is your entire setup. You can see that there is a cantilever beam. On the tip of the cantilever beam, this accelerometer is connected. The signal from the accelerometer is first sent to the charge amplifier, and from the charge amplifier, a cable is connected to your oscilloscope. When I am exciting the beam and allowing it to vibrate freely, there is a vibration signal on the screen which we are going to use to measure the damping. This is our aluminum beam. Let me excite the system. You can see that this is the output. To see it in a better way, I am compressing my time scale, and let me again excite the system. So you can see that this is the decay plot of aluminum. So this is my signal on the screen, and by changing the horizontal scale, I can contract or expand my time scale, as well as I can rotate this knob to increase or decrease the amplitude. But the current setup is okay for me, so I am just changing the time scale so that I can select my peak. Here you must note that in some of the cases, the decay in the amplitude will not be so sharp. That means you will not be able to take two consecutive peaks. So in that case, what we can do, we can select one peak, and then after 10 cycles or 20 cycles, or we can select the second peak, and by applying this, the logarithmic decrement. So for my case, I am selecting third peak from the left and the 10th peak from the left. Here I am putting my cursor mode in the match voltage, and from selecting the cursor A and cursor B, so let me select the cursor A. If I'll move the cursor A at the tip of my, so this is the tip of my third peak, and then I am selecting cursor B, and again I am moving the cursor, and this is on the 10th peak and this is on the third peak, and you can see here that the reading are, so I can check how many cycles I am taking in between my first reading and the second reading. So from third peak, when I will move to the fourth peak, actually I have moved from one cycle. So 1 2 3 4 5 6 7, I am moving 7 peaks ahead. So when I will apply the formula, my n value will be 7, and the two values are 420 millivolt and 1.12 millivolt. Using these two values, my logarithmic decrement will be. So don't you think that the logarithmic decrement is a wonderful tool to find the internal damping? And I hope through this experiment you have understood that how we can find the damping using accelerometer and oscilloscope. You can try the same experiment for different materials like wooden strip, plastic strip, and you can see which material is having larger damping. For example, if you are going to apply the plastic beam and the steel beam, what would be your opinion? Whether the plastic will have higher damping or the steel will have higher damping? Let me show you the output of a steel beam and a plastic beam. So this is my mild steel beam, and this is the vibration of your beam. This is the output of a plastic beam, and you can see here that as expected the damping of the material will be very high, so that we can see here that the amplitude decay very fast. In addition to that, we can also see that material is soft compared to the steel and aluminum. So when I will excite and I will see the free vibration frequency, the frequency of vibration is significantly less as compared to the frequency we observed when we check the steel and aluminum beam. So this is how we can measure the damping of different material using the given setup.